Welcome to Visionary. I'm John and I'm working on an FPGA replacement for the 6560 video interface controller in the VIC-20. This video is a history and technical description of the first prototypes that I have been working on. The prototypes are based on the DuPro Logic FPGA development board, which uses an Intel Altera Cyclone 4 FPGA. But that's getting ahead of things. The VIC chip in the VIC-20 is connected to a small video amplifier or buffer circuit, and from there to either an RF modulator to a television or to a composite video monitor. This is the circuit for the video amplifier. The two inputs from the VIC-6560 are the luminance or Luma signal and the chrominance or Chroma signal. This is the video circuit setup on a breadboard. I was very reluctant to cobble together something that might generate video or might generate something bad and then connect that up to my VIC-20. So I used this copy of the video circuitry instead and connected this to the composite in connector on my telly. There are a couple of extra capacitors to try to reduce the noise in the video signal. Breadboard is a terrible platform for use with RF signals, and so this is a version on stripboard that I used for all the initial work. It turns out stripboard isn't much better. FPGAs are digital devices. They speak zeros and ones. Composite video is not binary on and off at all, but is an analog waveform comprised of multiple analog signals all melded together into one complex signal. I have a video that describes the details of the NTSC composite video signal. There's a link up in the corner somewhere or down in the comments or something. To change the digital values from the FPGA into these analog wonders, you need to use a digital to analog converter, or DAC. Although the Luma signal is analog, it's not very analog. In the VIC it has only 6 discrete values: sync, blank, and 25% to 100% white in 25% steps. So we can use this most basic of DAC circuits. This is very much the way it would have been implemented within the original design back in the 80s, a chain of different value resistors with transistors that pull one point in the chain to ground. This works in this instance because the video amplifier has what amounts to a pull-up resistor attached to the output of this DAC, so grounding different points in the resistor chain results in different voltages on the Luma DAC's output. This is about as simple as a DAC can be. The FETs, field effect transistors, are configured such that when they are on, they are pulling their respective resistor to ground, but when they are off, that node is left to float at whatever voltage it finds naturally. This way, one node that is off isn't affecting the others. At this point, people that know a bit about FPGAs might be saying, why use the extra FETs? Why not switch the resistor chain directly from an open drain FPGA output? Well, the reason for the added FETs is that the FPGA's outputs are only rated to 3.3 volts, and given the wide tolerances of the various resistors in the video circuit, especially the variable resistor, it is well within the realms of possibility for the voltage at the FPGA to exceed this amount, so the FETs are there to isolate the FPGA from this voltage. Here's the initial prototype of the Luma DAC set up on breadboard. At this stage I used whatever random resistors I had to hand, sometimes having to wire 2 in series and sometimes 2 in parallel to obtain the values I wanted. The red and black wires bring in the 5 volt power. The green wire to the left is the Luma output signal. Those black blobs, they're the field effect transistors, and the rainbow wires bring in the digital control signals from the FPGA, only one of which will be active at a time, which is known as a one-hot signalling system. After convincing myself that this did work as intended, I moved this circuit onto a piece of stripboard as well, again to reduce noise in the signals. The other video output from the 6560 is the Chroma signal. This carries the colour information. The Chroma signal is a sine wave, and as such does vary over many possible analog values. and so the Chroma DAC must use a different implementation to the Luma DAC. The second simplest DAC to implement is an R2R network. Each of the 8 inputs to the DAC can either be pulled down to 0 volts or pulled up to 3.3 volts. Intuitively, if you consider the Chroma 7 input at the right hand side, you can sense that if it is at 3.3 volts, it will have a much larger effect on the output than if the Chroma 0 input at the left hand side is at 3.3 volts. And this is indeed the case. Chroma 7 has 128 times more influence than Chroma 0. Each tap along from Chroma 0 has twice the influence on the output. This 8-bit DAC can produce 256 values between 0 and 3.3 volts, which is kind of convenient as that just happens to match the voltage range I measured for real 6560s. Outside of the VIC chip, this output is DC isolated from the rest of the video electronics by a capacitor, so I'm not worried about the inputs going outside the 0 volts to 3.3 volts range. Whilst the Luma DAC does reflect how things would have been done in the good old days, this Chroma DAC definitely does not. The sound DAC is nearly identical to the Chroma DAC, except it needs 5 volts and so has level shifters to convert the 3.3 volt signals from the FPGA into 5 volts for the DAC. Here's the Chroma DAC laid out on a piece of strip board. And yes, it really is just a handful of resistors. This is the DuProLogic FPGA development board I've been using. It's based on an Intel Altera Cyclone 4 FPGA. Those of you who've played around a bit with Arduino boards might recognise the Arduino Maxi connector layout they've used. Those connectors aren't all aligned on the same 0.1 inch grid as one might expect them to be though, which is a pain in the bum when doing PCB layouts. I spent more time with calipers than I'd like to confess to, and still had issues, but more about that later. Initially, I was powering the FPGA from the micro USB connector, which is also how the board is programmed. But once I'd put together an interface board to the VIC-20, I could run the FPGA from the VIC's 5 volts supply using the 3.3 volt regulator on the FPGA board to provide the low voltage for that board. The 6x6 array of LEDs weren't particularly useful as they share I/O lines with the 36-pin connector, so I had to disconnect those LEDs using the jumpers provided for that very purpose. I did use the push switches from time to time though. Here's the initial hookup of the FPGA to the Chroma and Luma DACs, and then to the video amplifier board. The black wire from the video board goes to the composite video input of my telly, and the white micro USB cable is just supplying power. I have no idea why I've got rainbow wires going to the Chroma DAC instead of having it plugged directly into the FPGA board, but hey, it makes for a colourful picture. So, here's a question. What's the FPGA video equivalent of Hello World? This is my Hello World output. Stripes of colour varying from one scan line to the next. There's no connection between the FPGA and a VIC-20 at this point, so everything is generated within the FPGA. A whole lot of things must work for these to be displayed. The vertical and horizontal synchronization timing must be close to being correct. The Luma DAC has to be correct so the timing pulses get through at the right levels. The Chroma DAC has to be working well enough to generate a pretty passable sine wave. And the TV has to be set to the correct input. This is a hello again output. At this point, we still aren't connected to a VIC-20, but these are the correct colour values the NTSC VIC-20 uses. The slight grot between one colour bar and its neighbour is a combination of how terrible composite video colour really is and noisy video circuitry. Let's take a step back for a moment and assess what it is we're aiming for. This is the pinout of the 6560. 3 of the pins are easy to work with. VDD in the top right hand corner on pin 40 is the 5 volt connection. VSS in the bottom left corner is 0 volts, and NC on pin 1 in the upper left corner is not connected. So they're all good. So VSS is the source of electrons, the negative connection, and VDD is where the electrons drain away to, the positive connection. Pins 2 and 3 are the video outputs. Next to them there's a read-write signal. If it is high, then something in the system is doing a read. If it is a low, then the 6502 CPU is doing a write to something, but not necessarily this VIC chip. There is a 12-bit data bus, which is unusual for an 8-bit computer. The lower 8 bits are bidirectional. During the first part of a CPU clock cycle, the VIC chip uses these to read from video memory or the character ROM, and during the second part of the CPU cycle, the 6502 uses them to read or write, possibly to the 6560, possibly memory, or possibly other devices. Data bits 8 to 11 are inputs to the 6560, and are used to read from the colour RAM while the video memory is being read. Pot X and Pot Y are for gain paddles, and the last active signal on this side of the chip is the sound output. On the other side, we have 14 address lines, Phase 1 and Phase 2 CPU clocks as outputs, a light pen input, and the high-frequency clock inputs from the crystal oscillator. To interface to the 6560's socket on the VIC-20, I need to use 5 volt signals, but the FPGA I'm using only supports up to 3.3 volts. To not blow the snot out of the FPGA by exposing it to too high a voltage, I need to use level shifters. So the address bus, data bus, clocks, light pen, and the read-write signal all pass through level shifters. All of the address bus lines and the lower 8 data bus lines require bidirectional level shifters. The other signals just need unidirectional shifters. But I have used bidirectional capable shifters for all of them. This is the level shifter circuit that I used. If you are interested in the details of how it works, then there are some excellent articles about this on the web. Now that we've got Luma and Chroma outputs and level shifter inputs, we can hook up to the VIC-20 and see if we can generate something approximating the basic boot screen. Here's the FPGA board with the Chroma and Luma boards mounted on each side and a whole bunch of level shifters connecting it to the VIC-20. And there you go, 3,583 bytes free and no 6560 in the circuit. The bad colour is caused by a combination of poor viewing angle of the LCD TV, the white balance of my iPhone being off, and the yellowish room lighting. It was way better in real life. Once I'd got the output working using the breadboard, I moved the level shifters to strip board. However, this is where everything started to get a bit wobbly bob, and I reached the point where I spent more time fixing wires that had become disconnected than I spent making forward progress. So it was time to make a proper PCB. But before I could do that, there was one extra function of the 6560 to implement: reading the value of the gain paddles. There are 2 paddle inputs, named X and Y for no obvious reason, and inside these are a 470k variable resistor connected between 5 volts and a capacitor to ground. Depending on the setting of the variable resistor, the corresponding capacitor takes a longer or shorter amount of time to charge. When the charge on the capacitor exceeds 2.5 volts, set by the 2 voltage divider resistors, the output of the voltage comparator turns on, pulling the output low. Inside the FPGA is a counter that increments from 0 to 255, and when the voltage comparator turns on, the value of that counter is latched into the corresponding 6560 register for that paddle. When the next sample period starts, the 2 FETs are turned on for a short period to discharge the capacitors, and the counter is reset to 0. The resistors in series with the FETs are to limit the current through the FETs if the paddles are turned to 0 ohms. Here's my first PCB design. Is it not a thing of joy and beauty? However, there were problems with this board, making it unusable. The first problem was a poor choice of surface mount component size. I accidentally picked a size that was almost too small to see, which would have been very difficult for me to solder. However, this is the main problem. I didn't get the connectors in the right position. Most of them were out by 0.1 of an inch. So they missed their mark when plugged into the FPGA board. This is impractical to work around, as every pin on those connectors would have to have been a track cut and a green wire bodge, which meant I had to respin the board. This is Interface PCB 2.0. What you're looking at here is the KiCad PCB layout. The red is a top copper track layer, the green is an internal ground plane, there's an orange 3.3 volt power plane, then finally the blue bottom copper track layer. Here's an Interface 2.0 board being populated. The FETs don't exactly match the KiCad footprints, so if you're using SO23 devices and KiCad, pay attention to the dimensions of the footprint you're using compared to those on the datasheet of the device. I made it work, but each FET was a bit of a bodge, which irked me a fair amount. All the surface mount components were hand soldered. This is a finished interface board. Yes, the alignment of those LEDs bothered me too, so I did resolder them, so they were less wiggly. In the bottom left you can see the comparator and FETs for the gain paddles. Across the top there are a couple of 74 series chips for clock conditioning and shaping, and the lines of resistors are the 3 DACs and the series resistors for those wiggly LEDs. Here is the final Interface 2 board, sandwiched to the Cyclone 4 board and hooked up to my VIC via a 40-way ribbon cable. The FPGA cable terminates in a small adapter board with pin headers that plugs into a ZIF socket that is itself plugged into the 6560 socket on the VIC. I am on my third ZIF socket, as there is a great deal of swapping between the FPGA and a real 6560. I have 3 different 6560 chips, so I can check if a particular effect on the screen is specific to one chip or really a feature to be implemented. This is the end of the line for the Cyclone 4 FPGA board. It is impossible to buy those FPGAs at the same price now. They are end of life and they are physically huge. Instead, I've decided to focus on the FNX Treon T20. These are readily available, reasonably priced, and available in a hand-solderable 144-pin quad-flat package, as well as a space-conscious ball grid array.